Good morning, everyone. This is joint work with Maria Kyropoulou from the University of Essex and Erel Segal-Halevi from Maria University. So as it has been said before, cake cutting refers to the problem of dividing one perfectly divisible good among many agents who value different parts of the cake distinctly. This is an old problem, and it's an interesting problem because of two particular reasons. One of them is that it's a very interdisciplinary problem, so it has been tackled by computer scientists, economists, political scientists, and mathematicians. And the second reason that makes this problem interesting is that it has many real-life applications, and one of them that I find particularly interesting is the division of land. The main goal for the literature in cake cutting is to find a mechanism or a procedure that, for any cake, finds an allocation that is fair in a sense, and probably the most conventional notion of fairness is envy-freeness that has been discussed before, and that it just means that nobody envies the part that somebody else receives of the cake. The literature so far has constructed very clever procedures to achieve envy-freeness when dividing a cake between 2, 3, 4, or more people. But one problem of these procedures is that they are only guaranteed to achieve envy-freeness when the players behave as you tell them, more or less, behave truthfully, when they report their preference over the cake truthfully. In previous work by Bransey and co-authors, it has been shown that one of these famous procedures, called Selfridge Conway, to divide cake among 3 players, can generate an envious allocation when the 3 players lie. And this happens in equilibrium. So what we do theoretically here is to extend this result to show that in this procedure, you only need one person to lie to generate envy. And this happens in a sort of an equilibrium way. And this raises the concern that whether these procedures that are very, very clever, they could be applied in practice, because from the literature on applied mechanism design, we know that many people misrepresent their preferences in practice. So to clarify, to provide some insights to answer this question, we take cake cutting into a lab experiment. We divide. In a real-life experiment, we ask people to divide cakes using envy-free and non-envy-free procedures and check which procedures generate more envy in an objective way and which procedures are considered as fairer in a subjective way. To anticipate our findings is that in most of the cases, people actually misrepresent the preference over the cake, which of course it's a problem because our procedures only work when people do not misrepresent. But nevertheless, we find that envy-free procedures generate substantially less envy than other procedures, proportional procedures. And this is particularly important in the case of dividing cake among 3 players. We also observe that players are quite smart. They can learn the preference of their opponents in repeated interactions, and they can use this learning to improve the share of the cake that they receive. And we observe that also learning increases over time, but also envy decreases over time. In the final slide, I will also tell you something about the quality of learning that is far from monotone or very good. So this is our cake. It's just an interval, as it has been said earlier. People have preference over the cake. So for example, here the blue player values only the parts that have blue bits. The green player only values the green bits. And as has been said earlier, a way to divide the cake in an envy-free way is to just cut and choose. Here the player 1 will cut a 2, and the other player will choose the part to the left. Interestingly, this method also provides an envy-free allocation when the players are strategic, when they are very smart and know the valuations of the other players. So in this case, player 1 will cut the cake at 7, and he will make the other player choose the part to the left, and he will guarantee himself all the cake. Unfortunately, this is no longer the case, as I said, for dividing the cake among 3 players. The procedure for dividing the cake among 3 players is called Selfridge Conway and works more or less as follows. The first player will be asked to cut the cake into 3 pieces. These 3 pieces have to be equivalent, they have to have the same value. So in this case, at 2 and at 7. The second player, player green, will be called to cut the cake, the best part of the cake, and we'll have to make this best part of the cake as good as the second best part of the cake. So he will have to cut a bit of the best part of the cake to make it equal to the second part of the cake. Then player 3 will not have to cut anything. He will have to come and choose 1 piece. Then player 2, then player 3. No, player 3, player 2, player 1, sorry. Then the crumbles, the remaining of the cake, will be divided later. And more or less, here in this case, it will be so that player 2 will come and divide the cake into 3 pieces of equal value. Then player 3 will come, choose the player 1 and player 2. So it's more or less like cut and choose, but in an iterative way. Here we'll show the example that we provide in the paper to show that this procedure fails to generate an envy-free allocation with just 1 person lies. In the example, we have a cake that has 6 pieces, and the preferences are as follows. The players 2 and 3 have the same preference over the cake. If players are to behave truthfully, the first player will cut the cake at 2 and at 4, generating 3 pieces of equal value not only for him, but for all players. And he will guarantee himself a utility of 1/3 of the cake. However, player 1 could also misrepresent his preferences and cut at 4 at 5 and generate 1 piece of cake that has substantially higher value, 1 to 4. This will make player 2 now choose, cut the first part of the cake, so that this has equal value as the second highest part of the cake. So he will have to cut at 2, so that both parts have 1/3 valuation. Right, and then player 3 will choose one of these parts, then player 2 and player 1. And player 1 is already guaranteeing himself an almost as good valuation as what he was getting being truthful. He will in fact get more when we divide the crumbs, and we can show that he will guarantee a higher utility than being truthful. Importantly, he's envious of somebody else who gets a higher utility, but he's doing the best thing he could do for himself. So this raises the question that this Selfridge Conway procedure, despite how well constructed it is, could be actually applied. In the paper, we also have results about how much players can gain by being insincere. We show that there are substantially large gains, theoretically. So as I said, we take cake cutting into the lab. And what we do is players will have to cut the cake against the same people in 7 rounds. In the first 5 rounds, they will not see their opponent's preferences. They only see their preference over the cake, so like this. But in the last 2 rounds, they will see their opponent's preference over the cake. We do this so that we can see whether players can actually learn their opponent's preferences. Players will divide many cakes. So they will divide cakes using different procedures. They will use cut and choose for 2 people. They will also use cut middle, which is like cut and choose, but both players cut the cake, and we choose the middle point, and we cut there. For dividing cake among 2 players, they would use Selfridge Conway and other 2 procedures that are famous in the literature for being proportional, Dubin-Spanier and Naster-Banach. They will also divide the cake against 4 people using Naster-Banach, Dubin-Spanier, and even pass, but I won't talk about that today. Right. We have 136 participants that come to the lab, and we pay them according to how much of the cake they get. And we also spend a substantial amount of time explaining them the procedures in an easy way. So this is the platform that we use for the experiment. It has several features that I want to point out. One is that players get some explanation about the procedure. Again, players can use a slider to cut the cake, and they see under how much points they get for the cake. The total points is 120. Once they cut the cake, they see how much of the cake they got, and they also see how much of the cake the opponents get according to their own utility function. We do this so that they can evaluate envy. That's the experimental path. I'm going to jump into the results now. What do we observe? This graph shows how many misrepresentations of preferences we observe. The truthful behavior is in red. The insincere behavior that gets you higher payoff is in green. And the manipulations that get you lower payoff are in blue. So you see, in most procedures, in all procedures, there's a lot of misrepresentation of preferences. And in many of these cases, we also see misrepresentations that hurt you. So you think that the best way is to cut a bit to the right, but you cut a bit to the left. In general, okay, I will stop there. This raises some concerns about the applicability of MB3 mechanisms in the lab. Yeah?
So in cut and choose, was there another player that you're choosing, or was that done automatically?
Yeah, so sorry about that. In all cases, the player is playing against computers that behave truthfully. The player is the first player, so in cut and choose, he will be the one who cuts. The players are told that their opponents are players. They don't know the nature of the players. Sorry, thank you. So yeah, however, despite that we observe a large number of manipulations, surprisingly, we observe that MB-free procedures generate substantially less MB than their proportional counterparts. So cut and choose generates MB in 7% of the cases. Cut middle generates MB in less than 20% of the cases. And Selfridge Conway generates MB in less than 30% of the cases. On the other side, all proportional mechanisms generate MB in more than 50% of the cases. This difference is statistically significant. So this is surprising for us because there was no reason for that. Then we asked players what is their opinion about the fairness of the procedure. Most of them report that the fairest procedures are the ones that are actually MB-free. And when we ask them why, they give us answers that make sense for us. So for example, somebody says, I think the one with 2 sliders was the fairest. This is Selfridge Conway. Everyone received the same amount, at least in my scenario, as they were all divided equally. So the takeaway from this is that despite manipulations, MB-free procedures, and particularly Selfridge Conway, seems to work well in real life. Then we look at the learning over time. So here you see that players actually get a higher payoff over time. And this is because they learn their opponent's preferences. And they actually get all the learning even before they see the preferences. The quality of learning is not always increasing because they make mistakes. But in general, there's evidence of successful learning in cut and choose, in cut middle, Selfridge Conway, and some other procedures. Finally, I will tell you something about the quality of learning. This is to relate to a large literature in mechanism design or applied mechanism design. It has documented that the errors we observe in practice have some sort of structure. So in cut and choose, suppose that you're playing against an opponent that you don't know their preferences. Say that in the first round you behave truthfully and you could add 2, and therefore each party is valued 50-50. Then you cut the cake and you see that your opponent chooses the part to the left. If you are called upon to play again, where you would not cut the cake? So the reason is that you should not cut the cake further to the right, because if the player is already choosing left, if you cut to the right, he's also going to choose left, and therefore you are going to, for yourself, a smaller piece of the cake. So cutting to the right is a dominated strategy. Strictly so if it includes a bit of the cake that you want. We check how many players use dominated strategies in the rounds 2 to 7 in both cut and choose and cut middle. So what we observe is that around 40% of the cake cuts use dominated strategies. And we look at the number of players that are supervisional. That means that they never make a mistake, they never play a dominated strategy. Only 25% of the players are supervisional. And we would like to understand better the types of mistakes that we observe. And this relates to a literature in the EC community and elsewhere that has documented that players fail to play the best strategies for them. So to conclude, there is a concern, a real concern, and we show that misrepresentation of preference can destroy the fairness properties of real life of procedures. Nevertheless, we observe that envy-free procedures generate less envy in the lab in objective terms, and they are also considered as objectively fairer. We observe that there is evidence of learning in the lab, and therefore this could increase the risk of misrepresentations in repeated interactions. As a future avenue of research, I think it would be interesting to generate procedures that could guarantee UMB freeness, or at least some approximation of it when players are strategic. And we plan to repeat this experiment using cake division of players, real players against real players, to see the difference in learning and behavior. Thank you very much.
Question first of all, I guess I was wondering what's the order of magnitude of the payments that the participants were receiving? Was it like cents or actual?
We pay them £5 for showing up, and then we take 2 rounds randomly, and we pay them. So if they get 120 points, the maximum, we pay them £12. So the best they could do is £30. The average payment goes in around £14, and we also have results on the amount of time they take during the play, and we also have results for,
And I guess the other question was in the learning part that you asked. Were they told they're going to play against the same player, or, the learning, I mean, it makes sense, it's a repeated game, right? So were they informed that they're going to play, otherwise, to define it as a dominated strategy, you assume you're playing with the same person.
Right. We tell them that they are going to play against the same player. So they have incentives to start learning through experimentation. We do not tell them that there are computers, but it's kind of obvious because once they cut the cake, the computer chooses automatically. Now, when we program the next experiment, there is some waiting time.
Any other questions? No. Following up on the learning part, so if I understand correctly, you also show them the utility function of the other player. Right? And it's the same utility function every run. So I'm kind of surprised there wasn't more improvement in learning because, take out and choose, for example. So a big fraction of the players, a big fraction of the time, got less than 1/2. Right? So you get less than 1/2. I mean, you should realize after one time of making that mistake that if you could get at least 1/2. Isn't that surprising? Like, you need to expect a bigger improvement?
Right, that's true. And so one way to see that more or less players know what they're doing, I will argue somewhat differently. So for example, in cut and choose, the number of, when they know the preferences, which is in round 6 and 7, MB is generated in really few occasions. So they're all getting more than the sincere guarantee of payoff. So here, let's go to cut and choose. So if they cut truthfully, they will get 60 points, which is half between 120. But in general, their payment increases quite a lot to reach almost all of the cake. In fact, we put the preference in the experiment so that they are successful. There are incentives to misrepresent. And we do observe that, in general, they do quite well. For cut middle, the truthful was 90, and they also increased. So there's some intuition that they actually understand more or less how the procedures work. Thank you.
More questions?
So was the utility function of the player, was it generated by a computer, or does this player kind of provided this function?
No, we put the preference over the cake so that there were incentives to manipulate. Otherwise, we would not see anything. But it's interesting to which degree the results we observe are due just to particular preference profile. In our next work, we plan to just generate preferences randomly And maybe this will give us a better insight.
Is another question? Here the players are manipulating by cutting by themselves, right? So if you assume that the procedure works kind of first, so it always cuts in half, and then you allow your players to manipulate by just misrepresenting the utility function, do you think this learning will be worse? I mean, I would expect it if they had to count the procedure really.
I see. I'm unsure. There is certainly scope for many types of misrepresentation. And we observe that sometimes they don't really know that the misrepresentation is going to hurt you. There is this, just 30 seconds, there is new literature that looks at which kind of manipulations are more obvious than other. There's a nice paper presented in EC this year, and it would be interesting because, as you said, if you don't know, it's not clear that you should start manipulating your preferences because it could be bad for you. We'll look more into that. Thank you.
Okay, let's thank Josué again.